Hello everyone, welcome back to ptet.chemistry channel. So I am trying out something new in a response to the recent setback where I have to take down pretty much all my A-level chemistry tutorials, especially the one that involve full paper. So in this kind of tutorial, what I'll do is I will just state the year. So I'll do a March 2021 9701 paper, and this is a paper 2 component 2 for the March 2021 9701 is the Cambridge International A-level paper, even though it's for the Cambridge International curriculum. If you had a look at the question, which I am not providing here, and I can't tell you where to find them, but you can find them yourself somewhere, which I'm not telling you how to find them, but you can find them somewhere. This is a paper 2 component 2. Typically this is an AS component paper, which is usually covered in the first year of the 2-year A-level curriculum. But it's also taken by students who didn't have the chance or the opportunity to sit for the AS component, presumably due to COVID, and some exams were cancelled in some countries. I really don't know how this will work going forward, but here is the first of hopefully many tutorial videos that I will do. So again, it will have the label, the title, March 2021 9701, paper 2 component 2 for the Cambridge International A-level exam. So without further ado, let me get started with question 1. Actually, before I start, so I can understand that a lot of subscribers, a lot of viewers have actually chosen to leave the channel for various reasons, partly because the resources were taken away from them, but the channel, students survived before the channel even existed, and students will survive long after even the channel is gone entirely. However, the channel is still very much alive, and I am trying my best to keep the channel alive. So don't forget to click the button on the bottom right if you like the work as you go through the videos, if you like the work that I'm doing and my explanations. Thinking out loud really helps students to think for themselves. I can't underline and circle stuff as I do on the normal question paper anymore, but what I can do is I can explain, and I can verbally say some stuff, and with the paper in front of you, you can hopefully see what is important as well. Alright, so click those buttons on the bottom right to subscribe to the channel, and once I have more materials, I guess you can subscribe and share the channel widely with all your friends, chat group, juniors, seniors, etc, etc. And you can follow me at ptet.chemistry, that is ptet.chemistry on Facebook, Instagram and Twitter. And suggest to me how this kind of thing can improve going forward without infringing on the copyright issues, of course. Question 1, part A1 is about drawing a curve on the axis. So you're provided the empty axis. So I'm just going to draw the empty axis. This is a Maxwell-Boltzmann distribution diagram. Maxwell-Boltzmann distribution diagram requires you to label the x-axis as energy. Sometimes the x-axis is labeled as speed, because speed is velocity. Well, speed is considered as velocity in the context of chemistry, not in the context of physics. In the context of chemistry, of course, we can also think of it as kinetic energy. There's energy E, and then on the y-axis you have number of particles or number of molecules having energy E, with energy E. And what they want you to do is you should label 2 graphs. So they want you to label just one graph first of all. So it's just like this. So what happens is, it's not a symmetrical curve to begin with, and there are no molecules or there are no particles with 0 energy, because this temperature is not 0 Kelvin. In the question it said at a given temperature. At a given temperature. So you don't see the question here, but you will have the question in front of you. At a given temperature, temperature is greater than 0. So that means that there's no molecule with 0 energy, because temperature is greater than 0. Yet there are always some molecules with very high energy, and we should label on the x-axis at some point the EA, which is the label for activation energy. They also want us to label the curve T1. So if I label this T1, so the 1 is not subscript, and that should get you the full 2 marks. On the same diagram, so this is now A part 2, see above. So on the same diagram, you got to label a second curve to show at higher temperature. So I'm going to try and use a different ink. At a higher temperature than this, there are more molecules with higher energy, so the whole curve will skew, or it will shift to the right, and you will have lesser molecules having lower energy, and you will have more molecules having greater amount of energy, such that you have something like this. So obviously you can draw different variation of it. You don't have to draw it that high, you can draw it a bit lower, but what you cannot do is this must be lower than this, because now you have lesser molecules that have low energy, and this must be higher than this, because now you have more molecules that have higher energy than the original number of molecules having this particular energy at the lower temperature. So what happens is, this is graph T2, which they ask you to label, and that is at a higher temperature. The whole Boltzmann distribution curve will shift to the right in response to the higher temperature. But there will still be zero particle with zero energy. It's just that there are more particles with the energy greater than or equal to the EA, because the area under the graph is not just the new area, but includes the old area there as well. So that's pretty much quite direct and straightforward for a AS level question. So one part B, the Boltzmann distribution assumes that the particles behave as an ideal gas. They want you to talk about ideal gas assumptions. Ideal gas assumptions, there are quite a lot of assumptions, and they can be worked up to 4 marks perhaps. They just want 2 assumptions. So the first assumption that I always tell the students, the easiest one to think about is negligible intermolecular forces. So intermolecular forces is the force of attraction, of which you range in the order of severity or the strength, from van der Waals to permanent dipoles to hydrogen bond, usually in that order, but not always the case. Negligible means you can ignore it, so that means not very strong. So you're not looking at something that is hydrogen bond, which is one of the strongest intermolecular force there is. So negligible means almost nothing, so we are always looking at the minimum or the weakest van der Waals of all. The other thing that I can be thinking about is the particles will collide, obviously, but they will collide, the particles have perfectly elastic collision. So perfectly elastic collision is a phrase that is used to describe the idea is conservation of energy, so there is no change in energy upon collision. So there is no loss of energy or gain of energy. It's just perfectly elastic collision, something that physicists will have understood a lot more. And of course, there's also the negligible volume, as well as I forgot the other assumption already, but there are quite a number of those assumptions, of which this is probably the most important one. All right. So 1B part 2. So I think this is going alright for the time being without the question in front of you. But 1B part 2 is a calculation question. So it's ideal gas calculation question. So I'll start by writing PV equal to nRT. So PV equal to mass over mR, RT, where N is the number of mole for the gas. M over mR, this is mass of the gas in gram. This is mR, which is the molecular mass of the gas in gram per mole. This is molar gas constant, given the data booklet. This is temperature of the gas in Kelvin. This is pressure of the gas in Pascal, or in Newton per meter square. And the volume is the volume, V is the volume of the gas in meter cube. This question is asking you to calculate the pressure in Pascal, so I'll make P the subject. One of the most important thing that students should always do is rearrange to find what you want first, instead of putting in all the values, and then you'll be wasting time rewriting the value again, and you'll be confusing yourself with so many values. Whereas the most important thing is write down the expression you need first, and then think about what are the values that you need to put in. So let's think about the value that we need to put in. So what are we given? First of all, we have the mass of the gas that is given is 2.00 gram. I have to keep it in gram because gram, the mass of the gas in gram, divided by the mR of the gas in gram per mole will give me the mole of the gas. Okay, as you could see, gram over gram per mole will give you mole. All right, mole equal to mass over mR. This is the mass given in grams, so that one is nice and happy. R is from your data booklet, so it's 8.31 joule per Kelvin per mole of the gas. This is given in Kelvin, which then you know that temperature must be the temperature of the gas in Kelvin. You are given this temperature in degrees Celsius, 120 degrees Celsius based on the question. So it's 120 plus 273, giving you 393 Kelvin. Number 4, I can calculate the MR of the gas, but the MR of the krypton, which is monoatomic. So straight from your periodic table, monoatomic because it's a noble gas with no tendency to form molecule at all. That's just 83.8 gram per mole. In terms of the volume is probably one of the harder one because it's given in dm cube. You don't want the volume in dm cube. So you don't want in dm cube, you want it in meter cube. So what I could do here is show you how to get to the meter cube, just like I would in my normal tutorials. Okay, let me find enough space on the side here. Let's start with this idea that we have 1 dm. 1 dm is 10 cm because decimeter converted to cm is 1 dm equal to 10 cm. So I don't want the cm. What I want is the cm converted to meter. So that is 10 over 100 meter. So 1 dm is equal to 10 to the power minus 1 meter. If I cube both sides, so what I'm going to do on the left hand side, I will do on the right hand side. 1 cube is 1, dm cube is, well, dm cube. 10 to the minus 1 cube is going to give you 10 to the minus 3, that is meter cube. And just like that, I can get my conversion factor. 1 dm cube is 10 to the minus 3 meter cube. I will convert my 5 dm cube to meter cube by multiplying by 10 to the minus 3 meter cube. So now that you've got all of these in the right units, with this expression, you can just pop all of that into your calculator without writing them out because you already written out what each and every one in the correct units represent. And you should get, once you press into your calculator, I have done this on my calculator before, so I had this tutorial before, so I'm just looking at what I've done before, and this will go a lot faster rather than you hearing me click and click on my very classic and beloved calculator. So I'm giving my answer to 3 significant figure because if you look at the data, 2.00 gram is 1236 fig and the 5.00 dnq is 3 sig fig. So appropriate number of significant figure would have been 3 significant figure. Alright, so that's it really for this calculation question. So what I'm going to do is I'm going to move this up a little bit because I don't want the space to be running out at all. Alright, and that's not the end of the question yet. Moving on, we have 1b part 3. So what we have here is they want you to state and also explain. What are you asked to state and what are you asked to explain? They want you to state and explain the conditions. So the conditions there is a plural on it. So meaning to say you need to consider not just pressure, not just temperature. So there are 2 particular things that you need to think about. First of all, it's going to be high temperature where it will be ideal, and I think what I'll do is I will state and explain in the same sentence because it's a lot easier if I just explain the temperature straight away. At a high temperature, the krypton atoms have much more kinetic energy because they will move a lot faster at a higher temperature, so they will have more kinetic energy. If they have more kinetic energy, they can move faster, but they can also move further away from each other. If they move further away from each other, that means they will be further away from each other, therefore weaker intermolecular forces, weaker or negligible intermolecular forces. As we mentioned earlier, one of the assumptions of ideal gases is negligible intermolecular forces. If you make the krypton atoms further and further apart until they have much weaker or negligible intermolecular forces, then you can reach the point of ideality. The next condition will be on pressure. So we want low pressure. So remember, the pressure is force over area. So the force is how much force the particles exert on the wall of the container as it collides with the walls. So we can think about the gas or the krypton particles. Since I use krypton atoms just now, I'll use krypton atoms or the krypton particles. They will occupy bigger volume since you are at a lower pressure. If they occupy bigger volume with lower pressure, they will be further away from each other. So again, if they are further away from each other, we can be thinking about negligible intermolecular forces. Again, negligible intermolecular forces, which I probably don't need to write there again, because if I say further away from each other, it's the same as the top bit then. Alright, so moving on to the next part of the question, which is one part C. I really think this is going alright for the time being. I mean, with the question paper in front of me, but not showing you on the screen, which of course you will have the question paper in front of you, otherwise you don't have much idea of what I'm talking about. The title obviously says that this is a March 21, 9701 Cambridge International A-Level paper 2, component 2 paper, which I'm not showing at all. Okay, I'm just showing you the solution, of which, if you have access to the paper, it's not on me. Anyway, so you're provided with the energy profile diagram in these questions. So what you have is energy on the y-axis. You're given energy on the y-axis, and the units is kilojoule per mole. And this is the progress of reaction, which of course you could be given as reaction coordinate or extent of reactions. So far, you are just provided with this label called reactants, and they want you to complete the reaction profile diagram. So reaction profile diagram, since they provided you reactants instead of writing out the actual reactants, we will also follow the thing there. They provided you with delta HF equal to plus 60.2 kilojoule per mole, and they also provided you with EA equal to plus 385 kilojoule per mole. This is enthalpy of formation, which is also the enthalpy change for this particular reaction that they want you to draw. The reactants going to the products, this is an endothermic reaction. An endothermic reaction means the reactants absorb energy from the surroundings such that the products will have more energy than the reactants, so that the products have higher energy than the reactants because the reactants absorb energy in going to the products. So what we have there is that, and then I'm going to put in some label from the start to the end, from the reactant to the product. So that is your delta H. This reaction is formation, it's going up, it's endothermic, label the value. And then the other side, you also have this thing called activation energy from the start to the top of the peak. That is what you call activation energy, and you're given the value of plus 385 kilojoule per mole. Alright, such that you have the 2 marks in the back, provided you don't do a double-headed arrow. It has to be going from the start to the top of the peak, that's activation energy, from the start to the end products, that is your enthalpy change. Alright, one single-headed arrow and not double-headed arrow on both sides. Next one, 1C part 2. This is a classic essay reactions in terms of what you could prepare for it. They want you to explain in terms of activation energy. So you must have this point. You must have collision of particles, because if particles do not collide, then you are not going to get reaction. How an increase in temperature affects rate of a chemical reaction. So you have this thing affecting rate of reaction. So what I could do is, I could start by talking about what you would have known from your year 9 to year 11, or year 9 to year 10, sort of 14 to 16 years old, O-level or IGCSE chemistry, is to do with collision frequency. So as temperature increases, we can say that reacting particles will gain more kinetic energy, as we said earlier. As they gain more kinetic energy, they can move faster, and therefore they collide more frequently. So gain more kinetic energy, therefore move faster. And if they move faster, they collide more frequently. There's really bad handwriting, so I've been told previously that my handwriting was quite bad, so let's try and keep it together this time. In terms of the second reason, we need to talk about the idea of activation energy, as well as what happened in terms of the Maxwell-Boltzmann diagram, which I have drawn earlier. At a higher temperature, this whole graph will shift to the right, where the area under the graph represents the number of particles that have enough energy to react because they overcome the activation energy. These are the number of particles that have energy greater than or equal to EA. You can clearly see the area under the graph has increased compared to the one at lower temperature. That's why we get a higher proportion of effective collisions. And that's pretty much what I'm going to be talking about for my second point, which is an A-level concept based on the Maxwell-Boltzmann diagram. So also, as temperature increases, I don't want to go directly because they ask us to explain. So there are more reacting particles with energy. With energy greater than or equal to the activation energy. Therefore, proportion of effective collisions, so you can say more effective collisions. I'm going to use the idea of proportion of effective collision increases, therefore rate increases. All right, and that's the end of that 14-mark question. So it's all about rate of reaction. In question 2, so we have a chlorine gas. So this is a group 17 chemistry. In the first question, so how is chlorine used in water purification? So you will have learned about this as part of group 17 chemistry, as chlorine chemistry. So the question is about how it's used in water purification. But in terms of how I will explain it, I always like to ask students to simply write an equation. It's a classic disproportionation reaction with the chlorine in zero oxidation state, because this is chlorine as an element. And this will give you HCl, which is your first acid. This is hydrogen in +1 oxidation state and chlorine in -1 oxidation state. The other product is chlorine as a +1. Chlorine, it has a positive oxidation state or oxidation number. When it's bonded to something which is more electronegative than itself, there's actually Cl minus. But it's an acid with a Cl minus, so the product is actually HClO. This is called chlorate 1 ion. So this is chlorine +1. Is one of the most classic disproportionation reaction. You should have heard of these as part of your AS redox chemistry, or at least in the group 17 chemistry of chlorine. This is not with a base or alkali, this is just in water. So both of these things, the HCl and HClO, are strong acids. And if they are strong acids, they can kill bacteria. So they can kill bacteria or harmful microorganism, or harmful microorganism, actually, not all, and harmful microorganisms as a result of your very strongly or very highly acidic environment. In B part 1, you are asked on an equation for first ionization energy, and this is of chlorine. So what you know is that first ionization energy from the gaseous atom, giving you the gaseous ion, single positive charge. Ionization is to do with losing electron. First ionization energy, it goes from 1 mole of the gaseous atom losing 1 mole of electrons to give you 1 mole of gaseous ion with a single positive charge. So it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atom to give you 1 mole of gaseous ion with a single positive charge. And they want you to include stat symbols. So ionization energy has no meaning without the stat symbols, has to be all in the gaseous phase. The second part of the question asks you on first ionization energy of the period 3 elements. So you are asked about the general trend. So this is not a specific trend. So this is the general trend in first IE across a period, and this is across period 3. So we gotta always remember that there are certain things that you can prepare the essay for. Just because they ask you in paper 2, it could also come out in paper 4, where you know anything from AS can and will be asked in paper 4. So across a period, we need to consider the number of protons increasing first of all, and the number of protons carry with it what you call nuclear charge, because the neutrons in the nucleus are uncharged, so the nuclear charge entirely come from the protons. So more protons, nuclear charge increases. And then across a period, shielding is roughly constant. So you can imagine sitting in a cinema that you know, like if you are sitting in the same row and the people in front of you are the same, so you roughly experience the same blockage from the screen if you are seated in the same row. Shielding is roughly constant as valence electrons are filling in the same shell. So valence electrons are filling in the same shell. You have pretty much the same explanation even if you're explaining the general ionization energy across the second period. Last thing is obviously about the net nuclear charge effect. So the net nuclear charge is also known as, so you don't really have to use the net nuclear charge. You can straight away and use this thing called effective nuclear charge, which is not the nuclear charge. It's basically the nuclear charge taking into account the shielding. So this is what we call Z effective. If you use Z effective, ZEFF straight away, no one is going to know what it means except for you and your teacher perhaps. So it's always good to always specify what you're saying before you abbreviate it. So that will get stronger since shielding doesn't have much of an effect. And if that gets stronger, it means your valence electrons are held more tightly to the protons in the nucleus, and therefore first ionization energy would increases because it becomes harder and harder to remove the electrons. In terms of the sketches, which, you know, even if they don't ask you to draw, you should be able to sketch the trend. And as you know, across a period, the first ionization energy will increase, decrease, increase, decrease, increase, go all the way down. In terms of the third period, you know, there's sodium, which is in group 1, and then there's the small drop is between group 2 and group 3. Actually, I just remember because in A levels you don't really do the Roman numeral thing anymore. We still do it in our O level. Let me see if I can just erase this. I can't, so I will just write down group 2 and then group 13, and then there's group 15 and group 16. Remember the P3 and the P4 configuration. So this is going to be the group 18, and then you are back at group 1. Okay, oops, I don't want Roman numeral, I want the number. Okay, so that's it really for the 2-mark questions. The next bit is, so there's still question 2, part C1. There are 2 bits, the next part of the question. This is to do with thermal stability. Thermal stability means how stable it is to heat. So thermal stability of hydrogen halide, hydrogen bonded to a group 17 element. So it's state and also explain. So in this paper, you're still given access to the data booklet. So remember that what we are trying to do, we are doing these reactions where HX go to H2 plus X2. So we are breaking the covalent bond, the HX covalent bond. So, you know, down group 17, the halogen atom, X gets bigger as you have more field shell, gets bigger due to more field inner shell. So you have more field inner shells, therefore, well, bigger radius really because of the bigger size. So HX bond gets longer And it's stated in the syllabus that longer covalent bond means weaker covalent bond. So this is without even looking at your data booklet for the actual value, which of course you can, but longer covalent bonds down to group 17, weaker covalent bond, easier to break. So if it is easier to break the HX covalent bond, how stable it is to heat will decreases. So because it become easier to break, so the thermal stability of the HX will decrease because it's easier to break. I mean, I always like to think about explaining stuff out like that. I'm not sure about you, but it's always worked better for me and my students like that. It's just personal preference, really. Okay. Not too sure how good this is going at the moment, but we can think about this halide ion. The next part of the question, you have Cl minus, Br minus, and I minus. This is not given the question, but as you know, iodide is a pretty good reducing agent, so that is a stronger reducing agent. And you are reacting all of these with concentrated sulfuric acid. So in terms of oxidizing ability, so it's not given there, but I'm just outlining in terms of the explanation, is that we have oxidizing power. So actually I should probably go the other way because I want to show that the halogens are oxidizing agents. So the halogens are X2, so oxidizing power of the X2 halogens is going to be Cl2, Br2, as well as I2. And consulfuric acid comes somewhere in between chlorine and bromine. We don't know the actual value, neither am I interested in the actual value. All I'm interested in is where is it roughly between chlorine and bromine. So what we know is there will be a redox reaction between consulfuric acid and bromide and iodide, but no redox with chloride. Okay, so there's no redox. This is your idea. This one will have redox with consulfuric acid, because this one will have redox with consulfuric acid because consulfuric acid is a stronger oxidizing agent than bromine and iodine. So consulfuric acid can oxidize Br minus to Br2. It can also oxidize I minus to I2. In doing so, your sulfur here, this is a H2SO4 molecule, so the overall oxidation state of a compound or a molecule is 0 because it has no charge. You have 2 hydrogen, each of which is +1 charge, oxidation number. Sulfur, you have 1 of it, and then you have 4 oxygen, each of which is -2 oxidation number. These are all covered in AS redox. Sulfur is +8 -2, the sulfur there is +6. Since we say it's not a redox reaction with Cl minus, because consulfuric acid is a weaker oxidizing agent than Cl2, so what we're going to get here is just sulfur +6, and that's exactly what the question is asking you. What is the oxidation number of the HSO4 minus, and what is the oxidation number of the SO2, that's sulfur +4, and the other one is H2S, the rotten egg smelling gas. This is sulfur -2, because each of the hydrogen is hydrogen +1, +1, +1, -2, overall oxidation state is 0, +4, -2, -2, overall oxidation state of the compound is 0. Okay, we can of course work it out from HSO4 minus. So if I show you HSO4 minus is an ion. The oxidation number of an ion is the charge of the ion itself is -1, hydrogen is +1, sulfur, and then you have 4 oxygen, each of which is -2. So the sulfur there is going to be -1. Move the +1 to the other side is -1. Move the -8 to the other side is +8. You're going to get sulfur equal to +6. So whether you have H2SO4, which is sulfur +6, or whether we have HSO4 minus, the sulfur remains +6, because it's not a redox reaction because of what I've just outlined previously. Alright, and that is pretty much what they want you to explain for the next part. So this is question 2, C part 3. They're asking you why different sulfur containing products. Okay, so this is all about the different oxidizing ability of the halogens. So depending if you are here, this is a stronger oxidizing agent than this. but it's a much stronger oxidizing agent than this compared to between this and this. That's why with iodide, sorry, it can go all the way to sulfur -2 because there's a bigger difference in the redox capability, whereas here it stops at sulfur +4, giving you SO2 product because yes, it is a stronger oxidizing agent than Br2, but it's not going to go all the way to sulfur -2 because of the different ability. Okay, so they say in terms of the products, they don't specify for chloride or bromide or iodide, so they don't specify anything, so therefore I have to be general and explain for the whole thing: chlorine, bromine and iodine. That's how you interpret this kind of question. So corn sulfuric acid is a stronger oxidizing agent than Br2, and an even stronger one, much stronger one, meaning much stronger oxidizing agent than I2, but corn sulfuric acid is a weaker oxidizing agent than Cl2. Remember, when you want to talk about oxidizing power, we have to compare with the halogens. Therefore, corn sulfuric acid cannot oxidize Cl- to Cl2. Just for the 1 mark, I guess. Part D is asking you to explain or state what is meant by disproportionation. So earlier I talked about it when I talked about Cl2 dissolving in water to give you HCl and HClO. So we know it as a redox reaction, and just like that chlorine earlier a few minutes ago is where one species is both oxidized and reduced in the same reaction. So usually we will get one species get oxidized and another species will get reduced, but disproportionation is one species get both oxidized and reduced in the same reaction. And another classic disproportionation is basically the next question, where they ask you on equations between Cl2 and cold dilute NaOH. So this is a non-extreme condition. This is considered mild disproportionation, and what this will give you is this is chlorine 0. I should perhaps start with a different ink. Chlorine 0 in aqueous solution will give you HCl and HClO. Those are acids that can react with base, and they will give you a salt which is Cl -1, and a salt which is Cl +1. So ultimately what you will get, let me just move this a little bit to the side. Ultimately what you will get is this product called NaCl, because it's a salt, since the acid in solution will react with the base to give you a salt and also water. So you get NaCl, NaClO, and you will get H2O. Any equation you write has to be balanced. This is Na and Na. So I have two products that contain Na, so there's 2 NaOH. I have 1 chlorine, 2 chlorine, so 1 chlorine and 2 chlorine. I have 2 oxygen, 1 there and 1 there, and I have 2 hydrogen. This equation is nice and easy and balanced out. There's another equation which is to do with hot concentrated NaOH, and that one is much harder to balance, but it's not impossible, and that's what I'm going to show you now as an extra bit. As you know, I tend to go in a little bit into details about this kind of thing. Is that you will not get chlorine +1. Instead, it will go further, because this is extreme disproportionation. You will go all the way to chlorine +5. And because you want to go to a higher oxidation state for chlorine, the chlorine is bonded with more oxygen. Here is just 1 oxygen. So what you have here is something called NaClO3 +1 +5 -2 times 3. The overall compound has no charge at all. It's still sodium chloride, and you still get water. However, to balance this kind of thing is a lot easier if you use changes in oxidation number. This is chlorine 0. Chlorine 0 going to chlorine -1 is a decrease of 1. And then if I have chlorine 0 going to +5 is an increase of 5. you want to get changes in oxidation number to balance out, because it's a redox reaction. So you multiply this by 5 and you multiply this by 1. To get that to 5, I need 5 NaCl, and I need just one of these, because just one of it. Since I have that, my changes in oxidation number is now balanced out. Minus 5 total is balanced by plus 5. 5 sodium, 6 sodium, so I need 6 NaOH. 5 Cl, 6 Cl, so I need 3 Cl2. The changes in oxidation number is balanced, but now it's the atoms. 6 oxygen, 6 hydrogen. 3 oxygen, I need 3 more oxygen, so there's 3 oxygen there. Plus 3 oxygen give me 6 oxygen. 6 hydrogen, 3 times 2, give me 6 times 1, which is 6 hydrogen as well. This is under more extreme conditions, hot and concentrated NaOH. This is not what's asked by the question, but it is certainly within the AS level syllabus, which you're supposed to know. Question 2 hasn't ended yet, so E part 1, they want you to draw a diagram. They say a diagram, you gotta show all types of bonds. So this is all type of bonds in this molecule called Al2Cl6, one of the most common case study in your A-level syllabus as part of dative covalent bond. They did not specify dot and cross, they just say a diagram as long as you show the bond. So this is AlCl3, typically we draw them as such with 120 degree because 3 bond pair, 0 lone pair because aluminum is from group 3, 13 with 3 valence electrons, by the way. And then what happened is it's got an empty orbital because it's got 2, 4 and 6 electrons in the outer shell. So what happened is it can accept a pair of electrons from a neighboring chlorine as a result of this thing where you have 2 AlCl3 molecule coming close together, and what happened then is you use the lone pair there to donate the electrons there because that is dative covalent bond. So what I can do is I can label this. Let me use a different ink. So this is a dative covalent bond where both the electrons in the covalent bond comes from one atom, which is this chlorine, occupying this empty orbital which can accept a pair of electrons. So this is a dative covalent bond. And the rest are normal covalent bond where one electron from the chlorine is shared with one electron from the aluminium. So those are normal covalent bond. So normal meaning one electron from each of the atoms, and they are single covalent bonds. So what we know is one electron from each of the atom. So these are normal covalent bonds. Just for completion, this is normal covalent bond, and this is normal covalent bond. Okay, and that was just for 2 marks, just specify what is normal and what is the dative covalent bond as part of the AS level chemistry syllabus on structure and bonding. Let's see, question 2, E part 2. What would you see? Describe what would you see when AlCl3 with water. Okay, so what can we say here? And then name the type of reaction, name reaction. Very clearly we know there is a type of reactions called hydrolysis. So what would you see and what is the type of reaction? I'll probably do number 2 first. It's called hydrolysis because what happens is the AlCl3 covalent bond, this covalent bond, they will get broken in the presence of water and they will form something else. So this question is not asking about the equations, but rather what you would see. If I think about the reactions in terms of what actually happens, so AlCl3 plus H2O will give you AlOH3. This is aluminum hydroxide plus HCl. So what do we have here? Let's try and balance this equation. So you got 3 HCl there, and I should have 3 H2O. Then I'll have 3 hydrogen and 3 hydrogen, 6 hydrogen, 3 oxygen and 3 oxygen, like that. I've seen some books and also some sources that could also get the Al2O3 as a product, the aluminum oxide, as a result of the exothermicity of the reactions. The hydroxide could get dehydrated and you could get the aluminum oxide being formed, and I'm pretty sure that is accepted as well. So this is insoluble in water. in water. So you have water, this is insoluble in water, so this will come out as a white precipitate. And as I mentioned, this reaction is fairly exothermic, and HCl is a simple covalent molecule, so you get steamy white fumes. Okay, so in terms of the observation, what we will see is that we will get a white precipitate. So you're not allowed to use the term PPT as a short form or as a shorthand notation, not in theory paper. However, you can do that in a practical paper. So steamy white fumes are formed, and there's a part of that hydrolysis reactions where the aluminium chlorine covalent bond actually gets broken. What about question 2? F. So we have 0.020 mole of that plus excess chlorine, and you get a liquid chloride, and this liquid chloride is 0.020 mole as well. And this liquid chloride is ZClN. So if we think about it in terms of balance equation, then Z plus Cl2 give you ZClN. And remember that Cl2 is simple molecular, it's a diatomic molecule, so you want N number of chlorine atoms. So N number of chlorine atoms is what you want. The number in front multiplied by 2 will give you N. So let's say the number in front is X. So 2x must be n, so x must be n over 2. So I could go back and I could just do n over 2, because n over 2 times 2 will give me n number of chlorine atoms as per whatever the question has given you. So that is my balance equation really, and it will be useful in the second calculation bit. In the first part of the question, so there's basically just asking you on the bonding and structure. So there are two parts of the question. So it looks like it is a simple molecular structure, because a compound that is liquid typically will have low enough melting and boiling point. Low melting point certainly, that's why it's a liquid. It will already melted at room temperature and pressure, whereas if it is an ionic chloride, it will be a giant ionic structure. It will be a solid at room temperature and pressure. So in terms of the bond cannot be simple or giant, so it has to be covalent bond. So structure is not the same as bonding, and you have got to keep an eye out for that. So question 2, part F, part 2. So as we mentioned here, Z plus that give you that. If I rewrite that equation, and then we can start doing our calculation. So remember, this was in excess according to the question, so we're just going to use this value and this value for our calculation. It's at the moment is 1 mole is to 1 mole, so we can be thinking about 0.020 mole as given in the question, giving you 0.020 mole. I think that was what it says. Yep. So this is the liquid chloride, which is also 0.020 mole. What can I see here? When I add excess AgNO3, so Z giving me ZClN, and then they will give me AgCl. So ZClN would have n number of Cl minus. So n multiple of Cl minus in ZClN. So that is not right actually. Hang on, that is ZClN, and then upon AgNO3. What this will give you is this will give you NaGCl, because it's just one chloride there, and there'll be n multiple of it based on this. So I know 11.54 gram is for this, and I know about ZClN, which is 0.020 mole. So hopefully you can see that 1 mole of this will give you n mole of Cl minus. In AgCl, so you can see hopefully the mole of AgCl is to the mole of ZClN. So you get n mole of this. You have n multiple of it. This n here refers to mole or something. This n here refers to n multiple of these, as in the ZClN there here. And then the mole of it is 1 of these will give you n numbers of these. So there's that. And then on the right hand side would be my actual number of mole. Actual number of mole of AgCl is going to be the mass over the MR. So the MR of AgCl, straight from your data booklet. So the AR of Ag times 1 plus the AR of Cl times 1, you're going to get 143.4. So there is your mass over MR, which is the mole, the actual mole of AgCl. And your actual mole of ZClN is given in the question is 0.020. And I just need to work out the value of N, which is how many multiple of chlorine is in there. Put it into your calculator and you will get N equal to 4.02. So that is to the nearest whole number, that is just 4. And pretty much this should remind you, they didn't say it's a period 3 element, but this whole chemistry, if you go back to the beginning of, nope, they didn't say anything about this element at all, so we can't assume anything at all. But this can remind you of SiCl4, for example, which is simple molecular. Oh gee, this question is long. There's a part G to this question. So question 2, G. So this is straight onto organic chemistry mechanism. As you could see, there's initiation, propagation, and the final step, which is termination. So this is very clearly a free radical substitution reaction, which is a case study into the chemistry of alkanes, which have got no double bonds or any polar bond to react or to undergo substitution or that kind of reactions. Therefore, it's just free radical substitution. And the required essential condition will be the presence of ultraviolet, or what you call UV light, in order to initiate the reaction, to kickstart that reaction. So give the electronic configuration of the chlorine radical. So chlorine radical is not a cation, it's not an anion, it's just a chlorine radical. So what we have is 1s2, 2s2, 2p6, 3s2, 3p5. Is a third period element, so it's in the third shell, and you have 2 electrons in the S subshell and 5 electrons in the P subshells, and 2 plus 5 in the third shell. There's 7 electrons altogether, 7 valence electrons, 7 electrons in the third shell, which means it's a group 17 element, as it is for chlorine, and it's a radical without a cation, without a charge at all to represent a cation or an anion. Part 4 is identify the products of the step labeled propagation 2. So what is propagation 2? Propagation 2 is basically Cl2 plus dot CH2Cl. In terms of the products, if you follow the free radical reaction mechanism, this is a free radical plus no free radical, you will get free radical plus no free radical. That is because this in essence is what you call propagation. Propagation basically means radical plus no radical give you radical and no radical. So what happened with the products is that this radical will attack the Cl, and then it will form CH2Cl, and you get another Cl. So basically this is CH2Cl2. And when you attack the Cl there, what you will get is you will get Cl dot as well. So this is propagation because no radical plus radical give you radical and no radical. This is a carbon bonded to hydrogen, hydrogen, chlorine, chlorine, tetrahedral molecule. This is called dichloromethane. Dichloromethane. They said identify the products. So it's going to be CH2Cl2 and also Cl dot, because the question specify a plural thing with a products. All right. Name the type of reaction shown in the final step. The final step of the reaction is very clearly a termination reaction. Terminate is an English word that basically said to end the reaction. A free radical reaction ends when radicals and radical recombine. So you could see the radicals recombine. The radicals recombine to give you no radical. So you get no radical as your final product from radical recombination, and that is the only, there's the very sign of this step called termination. So in terms of another organic molecule that is a product of the reaction, so CH3Cl and Cl2 was this reaction. So far we said CH2Cl2 dichloromethane as the one of the product in propagation, as well as the product shown in the final step, which is the termination in the question. However, it says other organic product. They don't say the, they say suggest identity. Well, they did say the, but it's a suggest identity of another organic molecule. So the key thing there is molecule, and the other thing is organic. So you can't be saying things like Cl2, which is actually wrong because this is inorganic. So we can be thinking about further substitution. So think about further substitution. So far, you started out with 1 chlorine, you ended up with 2 chlorine and 2 hydrogen. So what we could do, example would be you substitute out another hydrogen and then you substitute that with another chlorine like that. Or you could do CCl4, which is completely substituting out the hydrogen, and there will be no more products. Okay. Of course, you could also consider that the radicals can recombine. So as you know, like CH2Cl dot can recombine with another CH2Cl dot. So there could be many potential answers to these, provided that you know what is right and what is not acceptable for free radical substitution. I would have gone for these two, which are nice and easy to think about in terms of the substitution. And that's the end of that 23 mark second question, which is quite long, and it's covered quite a lot of concepts covering inorganic chemistry as well as organic chemistry towards the end. So looking at question 3, what we have here is compound P, Q, and R. So I don't want to draw P, Q, and R because you have got the question in front of you, but you can imagine that if you have this group, this is called nitrile. I purposely didn't draw in the ion form because it's actually bonded to an alkyl group, to a carbon, so that is what you call a nitrile group. If it is a NC ion like this is called a cyanide ion, whereas this is a nitrile functional group. And then you also have this thing which is not really your A-level syllabus, but this is an alkyne functional group. So this carbon-carbon triple bond, I think they didn't really tell you it's alkyne, not that it matters, but then carbon-carbon is alkene. Okay, the first part of the question is basically on chemical energetics, which is an AS level concept. So given that these are, they give you the enthalpy change of formation, so what we could do is we could just say enthalpy of reaction. Since they give you enthalpy of formation, so there's just the sum of the enthalpy of formation. Make sure you always label what data you're given, and therefore depends what formula that you'll be using. I'm given the enthalpy of formation, so it's formation of products minus formation of reactants. So a lot of the times the students just do product minus reactants without really considering what information have you been given. In this question, you've been given formation and you want the formation of P. So P is that molecule called C4N2. So my enthalpy of reaction, they give me minus 2036. So that's just the enthalpy change of the reaction. And O2 is an element, N2 is an element. So you should know the formation of O2 as an element is 0. The enthalpy of formation of N2 as an element is 0 because it is N2 gas, this is O2 gas. N2, O2, gas and gas are what you say elements. Enthalpy of formation of elements are 0 because you are forming the elements from the elements in their standard state. So there's no change at all. So the products, you have 4 CO2. Enthalpy of formation of CO2 is given as minus 384. And then you minus the formation of the reactants. So you have 1 molecule of P. So there's just the enthalpy of formation of P. Okay. So what we have then is you could evaluate it, or you could just move this minus this value, move it to this side, and then move the minus 2036 to the other side. You're going to get enthalpy of formation of P. So that will give you minus 1536, which is from this, and then plus 2036. And that will give you an answer on your calculator, which doesn't show you the plus sign because your calculator doesn't show the sign when it's positive. But with any topics that require energetics, for example, physical chemistry, you gotta have sign, value, and unit. So that's very, very common there. Sign, value, and unit. This happen to be endothermic change. So your calculator will not show you that at all. Part 2 is about the lack of reactivity of nitrogen. So we got the nitrogen triple covalent bonds. They are very strong. And they are strong covalent bonds. You need a large amount of energy in order to kickstart the reaction. So large amount of activation energy. To kickstart the reactions to overcome. Need large amount of energy in order to overcome the activation energy. Okay, so you need to break that triple covalent bond before you could react it further, and therefore you need a lot of energy to overcome that strong covalent bond. So part B, so this question is I lost track of it, so it was question 3. 1 and 2 was fairly long actually. Question 3B part 1. So there are 2 parts to the definition, so that's why it's 2 marks. They want you to define weak Bronsted-Lowry acid. So a weak acid dissociates partially. So weak acid dissociates partially. A Bronsted-Lowry acid is a proton donor. So we can be thinking about a weak Bronsted-Lowry acid dissociate partially. Some people don't like the word dissociate. You can use the word ionizes. Just choose either. So just choose either one. We say partially. Some people don't like partially. You can choose reversibly. Again, just choose either one. But the next one, you can't really choose it. It has to be H+ ions because these are the hydrogen ions in solution in water. Dissociate partially into H+ ions in water, or dissociate I can't think of another definition really. I mean, partially, reversibly has to be there. So this is a H+ donor. A H+ donor is the definition for Bronsted-Lowry acid. Alright, just for the 2 marks definition there. Next bit is on structure and bonding. So they want you to just have a label diagram. So make sure you see this kind of question. So make sure it's label. And you got to talk about pi bond. Pi bond is a sideway overlap. They said that triple bond, when you get triple bond, what you have is 2 pi and 1 sigma, because you can only form a maximum of 1 sigma due to the head-on overlap. So what happened is, this is the head-on overlap, and you will get a sideway overlap, which is that and that. So if I use a different color ink, that and that is a sideway overlap. So what you will get is this and this. So that is your pi bond. So that is due to sideway overlap. Okay, and these are actually the unhybridized p orbitals that overlap sideway. They are actually 2 pi bond. You could have gone for the other one. The other one is actually in front. If I show it in 3-dimensional, it's going to look like this. So it's coming out from the paper, from the screen, towards you and away from you. This is in the plane of the screen, in the plane of the paper. So again, there's a sideway overlap. So this is a bit hard to draw. I'm trying to draw in 3-dimensional. So this is flat. One is coming out towards you, one is away from you. So that one is the pi bond. This is considered 1 pi bond, and the top one is considered another pi bond. So you can choose whichever one you want to draw. I would have gone for this one because it's very much easier to draw. The next bit is on infrared spectra. So not only they want absorptions, so it's absorptions because it's plural and there are 2 parts to it. They also want the bonds. So this is straight from your data booklet that you can manipulate and see what value you're expecting. So first of all, as mentioned, we have a carbon-nitrogen triple bond. This is C triple bond and nitrile. Straight from the data booklet, you have weak absorption. And this is straight from the data booklet again. You are asked to predict where would they appear, based on the data booklet. The other one is C triple bond alkyne. I'm not sure if they actually wrote down alkyne in the data booklet, but they would definitely have this carbon-carbon triple bond. They also mention whether it's strong or weak in the data booklet. The syllabus is changing a little bit for the upcoming 2021 syllabus. So question paper might be slightly different going forward. So if I'm not mistaken, they'll actually provide the data in the question paper itself, so it won't be that too big of a difference at all. Let me start a new page for the next part of the question. So this is still question 3. This is D, and they want you to look at reaction 1. So I'm not going to draw the reaction scheme here because of whatever happened previously. So I'm not showing the question. You have the question in front of you. We have an alkene carbon-carbon triple bond. We have a nitrile. C triple bond N. So the fact that you have this thing called unsaturation. Saturated means the carbon doesn't have any multiple bond. They're all carbon-carbon single bond. Unsaturation means there's carbon or carbon has multiple bond. Okay, carbon with multiple bond. So you can think about addition reaction. If you have unsaturation, you can have addition reactions. I don't know why I put the in apostrophe. I don't really need that inverted comma at all. So I can hopefully you can see reaction 1 is an addition polymerization. So when you look at equation scheme, not necessarily it is what we are answering the question, but you gotta look at it and identify from the reactants and conditions. So in the polymeric chain, as shown in the middle, you have nitrile along the polymeric chain that it will get hydrolyzed in the acid hydrolysis, H2SO4 and reflux. So there's acid hydrolysis of nitriles, and that will give you carboxylic acid as part of the polymeric chain. Reaction 3 is just adding hydrogen across the alkene as well as across the nitriles. Okay, so it's just what we can say reduction is what I believe as reduction, but some textbooks, some teachers will have called it addition. Technically it is reduction because both carbon and the nitrogen will have gained hydrogen atoms. Gain of hydrogen in the context of organic chemistry is what I call reduction. And reduction of the C triple bond N is also called reduction of nitrile to give you amine, and that is A2 chemistry. They actually didn't ask you the product here. They actually give you the product as the amine. If you look at product T is an amine, so nitrile to amine is actually reduction as well. But they don't ask you that particular reaction itself on the until A2, I guess. Anyway, I don't know what I'm talking about. Part 1, sorry. Name the type of reaction shown in reaction 1. I already did, so I can just copy paste that. I mean, when I see the question, I would have scribbled some stuff on the question itself because they only mark the answer. So it doesn't hurt to scribble some stuff, so that you get reminded when you actually do it later on as part of your brainstorming. Reaction 2 was your acid hydrolysis of the nitrile. So what I'll do is I'll copy the polymeric chain, which is C, 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 H and H, H and H, but no longer Cn. Now I will have CO2H because it is now a carboxylic acid. The nitrile has undergone hydrolysis, acid hydrolysis. They didn't ask for structural or skeletal or whatever. You could leave it CO2H. You could have drawn display. You could have drawn, I don't think you could draw skeletal because the actual thing that was given as part of the polymeric chain was actually display in such a way. So you could choose to draw display here, or you could choose to draw structural as I've done there, which should be alright, I think. Part 3, you're asked to name compound T. T is CH3, CH2, CH2, NH2. So this is an amine. And you have got 1 carbon, 2 carbon, 3 carbon. 1 carbon, 2 carbon, 3 carbon. So this is called propyl for 3 carbon. This is called propylamine. In part 4, T is also formed by reacting this thing, which is 1, 2, 3. To give you that, And remember that this equation is not balanced. By right, you would need, what do you need? You need this, NH3, and then you get HBr. So your necessary conditions. So they say they give you this one, but they want you to put down the conditions. So there is a plural there, so be very careful even though it's 1 mark. So don't forget that you need concentrated NH3. Your solvent has to be in ethanol. Okay, so this is the solvent that you use in order to have this reaction going at a favorable under favorable condition, and you gotta heat this under reduced pressure. Okay, so this is not a reaction to be reflux, but it's to be heated under reduced pressure. These two are the absolute conditions. They are required to stop at single substitution. You also use concentrated ammonia. Next question, I think question 4 is the last one in this paper 2 series. So they want you about bond angles. Bond angle is to do with shape, or you can say geometry, and that is down to valence shell electron pair repulsion theory. So I have a look through. I no longer have a topical playlist, but I do have A-level concepts tutorial videos from a while back that I explained very thoroughly on the VS EPR concept, something that you would need to master because they can ask you in multiple choice, they can ask you in structured questions such as these 2 marks question here, or they could even ask you in paper 4 if they want to. All right. So what we have is HOCH, HCOH. So ideally speaking, I could be, coming up with this example myself by right. Okay, I'm not saying anything. This carbon have formed 4 covalent bond. These are 4 single covalent bond. This is sigma, 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 sigma. So this carbon there has 4 sigma bonds. So there is 4 bond pair. Bond pair, I'll just abbreviate this BP. Carbon with 4 outer shell electrons form 4 bond pair, therefore a 0 lone pair. That is all the 4 bond pair repel equally. You're going to get tetrahedral, and you're going to get 109 degree tetrahedral. Okay, and that is your X there. It's going to be 109 there, 109, 109, 109. So a lot of students, they will have, I don't know, probably put down 90 degree because it looks like 90 degree, and that's a way to confuse people who know and people who don't know. That is your Y. If you look at that carbon has 1 sigma and 1 pi. Remember, this is a double bond, so it's 1 sigma and 1 pi. You count the sigma bond, 1 sigma, 2 sigma, 3 sigma. So you have 3 sigma, therefore 3 bond pair. You got 0 lone pair because you actually use the other electrons left on the carbon to sideway overlap, just like the earlier question, to form a pi bond. That's why you have 0 lone pair. So when 3 bond pair repel equally, you're going to get trigonal planar geometry. And trigonal planar geometry has a 120 degree bond angle. So Y is equal to 120 degree. And X was 109 degree for tetrahedral geometry. Part B, we have hydroxyethanol. I think that was hydroxyethanol, wasn't it? So you have HO like that. There's hydroxyethanol because this is 1 carbon, this is 2 carbon. Hydroxyethanol, ethanol for 2 carbonaldehyde, more important priority group. Ethanol, less important group, hydroxyethanol. What would you observe? This is a primary alcohol because the carbon with the OH is bonded to one other carbon. This, on the other hand, is what you call an aldehyde, but you name it as alkanal. So with 2,4-dinitrophenylhydrazine, you're going to get a condensation reactions, and you will get an orange precipitate forming. And that orange precipitate is a result of a condensation reaction, which is actually stated in the syllabus as well as in the Cambridge textbook. So they could ask you for, what is the name of that type of reactions, and you got to know what is going on there because it is in the Cambridge syllabus as well as the Cambridge textbook, right? Tolerance reagent. Tolerance reagent is basically silver with 2 ammonia with a plus. So this is a colorless complex. You will learn more about complex in A2, transition metal chemistry, but it's a colorless solution. When you dissolve silver chloride in excess ammonia, this is a colorless solution. The ammonia has 0 oxidation state because the molecule is a compound. your silver is +1. With aldehyde, the silver +1 will go to silver 0, only with aldehyde, not with ketone, not with alcohol. So what you will get is you will get a silver mirror, which is basically silver in 0 oxidation state that forms as a result of the aldehyde getting oxidized by this oxidizing agent. The oxidizing agent itself get reduced from +1 to 0, giving you the silver mirror. Part C, so you have a H plus Cr2 or 7,2 minus, and that obviously is an oxidizing agent. As you would have known, we use it to oxidize alcohol, primary alcohol to, aldehydes. If you heat and distill immediately, it will give you carboxylic acid if you reflux it from primary alcohol. It will give you ketone if you oxidize secondary alcohol. What we have here is a primary alcohol. So hopefully you can see HO and aldehyde. So what happens there is you get carboxylic acid because this is a primary alcohol. This is an aldehyde, CHO, that would also give you carboxylic acid, just like that. Okay, so this is called ethane dioic acid because it has got 2 carboxylic acid there. Okay, state and explain other necessary conditions for the reaction to be successful. As mentioned, you need to reflux it. You cannot heat and distill because you want to ensure complete oxidation of the primary alcohol. This is the primary This is the primary alcohol. This is the carboxylic acid. You want to ensure complete oxidation. You don't want to have partial oxidation, which you can get if you heat and distill immediately. You can stop at the aldehyde stage. So reflux, and then needed to ensure complete oxidation of primary alcohol, basically the hydroxy group to carboxylic acid. So it's only 2 marks and they say explain, right? Otherwise, if heated and distilled, can get aldehyde instead. So meaning to say the primary alcohol doesn't get oxidized all the way to the carboxylic acid form. So I'm just going to leave that out a little bit so that I have a better use of the space there. All right, and that's not the end of the paper yet. Oh, gee, I didn't realize that paper 2 is this long. This is question 4. This is D, part 1. We're going to use all these square bracket H to represent hydrogen atoms for the reduction of that species. So you have H, and then I'm going to reduce that species, write out the structural formula. CH2OH written from left to right, HOCH2, and then CHO for the aldehyde. And then you are going to get the, what is this? HOCH2, CH2OH. It looks complicated like this. It might be a lot easier for the sake of balancing question. I just use molecular formula. C2H2, 3, 4, 5, 6. And then there's O2. And then there's C2H 1, 2, 3, 4. So there's 4 and then O2 plus H like that. So 2 carbon going to 2 carbon, 2 oxygen going to 2 oxygen, 4 hydrogen going to 6 hydrogen. I need to add 2 hydrogen. So this equation is balanced now. All right. So I don't really need to show structural formula. In fact, in balancing equations involving this kind of thing, it's a lot easier to use molecular formula because it's easier to count that way. So we're going to do reduction of that aldehyde back to, based on the scheme given the questions, you're going to reduce the aldehyde back to the primary alcohol. So we need a reducing agent, and a reducing agent is LiAlH form. This is called lithium aluminium hydride. Hydride is basically H minus, and is very, very sensitive to water. So that's why we use it in dry ether. Okay, ether is a solvent. Usually we use this thing called diethyl ether. So it's you can get it dry so that it doesn't contain any water at all. Not that it matters that much. But as long as you get LiLH4, I'm sure you have gotten the answer correctly. So now when we have alkene A, so they're saying that you get an alkene A can give you this thing if you do cold dilute acidified manganate 7. This is manganese plus 7. It will go from purple to colorless because you oxidize the alkene. Alright, so this is mild oxidation of the carbon-carbon alkene. If you see carefully, you have 2 carbon to begin with, so we can just imagine that we have, therefore A is CH2, where I've added OH there and I have the OH there because I form a diol if I use cold dilute acidified KMnO4 onto this particular alkene. But the question say name. This is formula. If they say state the identity, you could give the name or the formula, but they want the name, so I'm going to give the name, which is ethene. And that's the end of the 10-mark question, and I think that's it really. I mean, there's no more to this question. Yeah, I mean, we reached the end of that tutorial. This particular tutorial, not too sure how exciting it is, but you know, I have written an empty screen, basically outlining the steps and how I would do it if I am to do it in an exam with the paper in front of me, of course, but I am not sharing the question paper, neither am I sharing any link at all, so you know, don't say I share anything with you apart from how to do the questions, which of course if you are at a Cambridge Center, you would have known how to get the question paper, not from me, of course. All right, so thank you for watching, and thank you for your supporting this channel, as well as, you know, not telling everyone in advance that I had to delete all those contents. But yeah, thank you for your support, and click the button on the bottom right if you found this useful, and let me know on how I can improve on this new venture into these kind of tutorials on my channel. I might wait for a little bit before I go a lot into new content, just in case that they will find something else to complain about this again. All right, follow me at ptet.chemistry on Facebook, Instagram, and Twitter, and look forward to hearing from you how this looks like going forward. Right, see you in the next tutorial video.